Good morning, Mr. Lin here, talking physics, and this week we're learning about position time graphs and velocity time graphs. Last week we made a motion diagram which is similar to a graph but definitely different. On a graph we have a causative agent, independent variable, dependent variable. With our motion diagrams, we had our reference frame, which was kind of the background with our marble drop lab. We used a meter stick as the y-axis, and time was not on an axis. We were interested in really taking snapshots of the object through space to describe its motion. What we're going to do a little bit differently with time this time around is we'll plot time on the x-axis like some of you were wanting to do. Well, now we'll actually start doing that. And so when I see a p versus t graph here, what that means is my position is going to be on the y-axis and my time is going to be on the x-axis of the graph. And so this is information coming from the physics classroom. It's a website that we'll use a fair bit in this class. I might substitute some readings from this website for those of you guys who don't have textbooks. And there's lots of cool interactives that you can do here if you want further enrichment. So let's go down here to this diagram. What we have here is a little car which is driving to the right, it looks like. And we can see this is a motion diagram, right? We have equal time intervals. And it looks like our distance covered is the same in each second. So we could say right off the bat that our velocity here is 10 meters per second. And we would also have to say that it's 10 meters per second to the right, or the positive x dimension. So when I want to turn this motion diagram into a graph of the motion, I plot time in seconds on the x-axis, and I plot position on my y-axis. And so each point from my motion diagram is going to turn into a data point now on our graph. So at time is 1 second, I traveled a distance of 10 meters, which we can see from that's a data point right there. And time is 2 seconds. I'm at my position of 20 meters. And so if we collect data, which we'll start to do about moving objects, we can plot that in this fashion. And if I connect all those dots, we end up with a straight line. And that tells us some important things about this motion. But before I tell you, why don't you think about it? Slope, as a quick review, is rise over run, this line. And so I go up 10 and over 1, my slope is 10. What does that actually mean with respect to the motion of the object? And I'll let you think about that. So our equation to calculate slope is rise over run. 10 divided by 1 is 10. Our units on the x-axis, y-axis, are meters. And my x-axis are seconds. 10 meters per second. That's the speed of the object. Key point. The slope tells us the speed at any point along this line. Is the speed changing? No. I have a constant slope. So we would say this car is traveling at a constant velocity. We could also say it's traveling at a constant positive velocity, so my direction is in the positive dimension, and that gives us a sense of what this graph means. So what you guys are going to need to be able to do is interpret graphs like this, or create graphs like this of motion. Let's go down to this motion diagram here. I have my position values, I have my time values. This one looks a lot like the one we created with the marble drop, except it's on the x-axis. And right away we see, okay, it's covering more distance in every second. We talked about that last week, which was acceleration. The speed is changing of this car. And so what does that look like on a position time graph? Well, here I'm plotting my position at 1 second. Here I've gone a couple meters. There's my first data point. At 2 seconds, now we've covered 8 meters. So my second data point is right here. And you'll notice when I connect the dots that we form a curved line. And that tells us some important things. First of all, we can say, okay, what direction is the object moving? Well, we're going up on the y-axis. Time isn't really directional, so we're moving in the positive dimension, whatever we've specified. Here it's to the right. And we can also say something about the speed of this object, this car. And we know now that the speed is changing. And so how do you get the slope of this line if it's curved? Well, we can calculate the slope at a position by drawing a tangent line to this curve. So if I were to draw a line here, tangent to the curve at that point, hold on, let me do that. Okay, so I sketched out this position time graph, and we're trying to figure out the slope at a point here. So we would draw a line that just touches the curve at that point, and then we would calculate the slope of this line. We would do the rise divided by the run. And that would tell us the instantaneous velocity at this point right there. And we can see if I were to draw a tangent line over here to my curve, the slope of this second line is going to be steeper than the slope of this first line. Therefore, the instantaneous speed is greater here than it is here. So we're speeding up, and hopefully that makes sense. Okay, back to the web page. We looked at this curving line. We now know that the speed is changing. We have acceleration happening, and we would need to calculate the slope at each individual point to find out the velocity. Those of you guys taking calculus, you'll learn how to do that this year to calculate basically limits as our time interval approaches 0, instantaneous time for my run. What would the rise be as x approaches 0? But for algebra-based physics, we won't really have to do that. Most of this you'll have to conceptually understand. Like I could give you a graph that looks like this, and you tell me what's going on. Well, there's the answer. We have constant velocity. You know that because we have a straight line. And here we have changing velocity, positive dimension, and we have that acceleration that we talked about. So slope is a big thing. Slow versus fast motion. Take a look at these two. The slope of this line is smaller than the slope of that line. What does that tell us? Well, this guy is going faster than this guy. So we have to kind of imagine the situation that's playing out, from these graphs. What if my slope is negative? So here the position is decreasing as time goes by, and I know I'm still moving because my position is changing. But how do I deal with a negative slope or a negative position change? Well, we just have velocity moving in the negative dimension. It doesn't really, the slope will tell us the magnitude of the velocity still, whether it be positive or negative dimension. But if I'm trending downwards, it means I'm moving backwards. Here, we're moving backwards, but we're doing it faster because the slope of that line is a lot steeper. Getting even more complicated. Slow to fast. How would we show that? Here I am. I'm starting the timer. Boom. I'm at some position out in space. Let's say it's 5 meters down the track. If I'm going like this, my position is approaching 0, so I'm coming back to the starting line. So I'm moving backwards, first of all, due to the negative slope. And then we have that curving line going on again. The curve is telling us that the slope is changing. And so we're either speeding up or we're slowing down. What do you think? Is the slope getting steeper or less steep? Well, it's getting steeper, so we're moving in the negative dimension and we're speeding up. Moving in the negative dimension, whoa, what's going on here? Going fast at first, and then my slope is getting less steep, so I'm slowing down. So I'm starting, I've turned around, I'm coming back to this towards the starting line fast, and then as I get closer to the starting line, I'm slowing down. Kind of an interesting thing to think about if you haven't looked at these before. Here's a couple practice. Why don't you guys take a minute and see if you can do this. Use the principle of slope to describe the motion of the objects depicted by the two plots below. Be sure to include information, blah, blah, blah. Okay, just tell me what's going on here. There is the quick quiz answer. The object has a positive rightward velocity, and the object has changing velocity. It is accelerating, so it's moving from slow to fast. If you said that, good job. This is basically the opposite. Object has a negative leftward velocity because of the negative slope. The slope is changing because it's curved, and this time it's going from slow to fast. I think that's a good place to stop. The next video, we're going to start putting velocity on the y-axis and see what happens then. Okay, have a good day.